Hello, ladies and gentlemen, and welcome back to more of the 2007 Grade 7 Gauss paper. So you can see we've got it right here before us. If you would like a copy of this contest, you can click the very first link in the description. Try these questions out for yourself. But question 15, how many positive whole numbers, including 1, divide exactly into both 40 and 72? Okay. So what we're really doing here is we're counting the numbers. We want to count all the numbers. We're going to call them D's, so that D divides 40 and D divides 72. Okay. Now these are common factors. They are things that divide both 40 and 72. So we'll make a note of that. These D's are called common factors. And you've likely heard before that there's a greatest common factor. Okay? So there is a greatest one, and the nice thing about it is each of these D's also divides the GCD, or greatest common denominator, sometimes it's GCF, greatest common factor, of 40 and 72. So, and if a number divides the greatest common factor, it divides 72 and 40 as well. Okay? You could even say something like, let G be the greatest common divisor of 40 and 72. We'll deal with what that number is in just a moment. If D divides G, well, G divides 40 and G divides 72. So if D divides G, then D divides both 40 and 72. Okay? And if D divides these, well, it can't be bigger than G. It's going to have to divide them. So if D divides 40 and D divides 72, then that tells us that D divides our greatest common divisor. Okay? So these are nice, wholesome math facts. So I just want to count the number. So we need to... By the way, you could also do something like list out the divisors of 40 and 72. I'll show how to do that in a moment. I feel like we're getting too deep into some math theory here, but I wanted to show this off because it's a useful technique. So we just need to count the number of divisors of the GCD of 40 and 72. That's what we need to do. Well, how can we figure out the greatest common divisor of 40 and 72? I have no idea what it is. I think it's 8. But how can we do that? Well, if we write 40 as its prime factors, so 2 cubed times 5 to the 1, and we write 72 in terms of its prime factors, 2 cubed times 3 squared, because it's 8 times 9. If we just take a look, what are the common primes here? Well, they both have 2's, but 72 doesn't have any 5's, and 40 doesn't have any 3's. So the GCD here is just going to be the highest power of 2 that is common to both of them. So it's 2 to the 3, or 8. Okay, well, how many divisors of 8 are there? Well, once we have it written in prime factorization form, if you just take each of the exponents, not the primes themselves, but each of the exponents, and you add 1 and multiply them all out, we don't have any others, but if it were something like 2 squared times 3 to the 3, I can tell automatically that this has 2 plus, let's change it to 5 to the 3. We take a look at the exponents. It's 2 plus 1 times 3 plus 1, which is 3 times 4. This number here, 2 squared times 5 to the 3, has 12 factors. Okay? This is a nice, useful technique. So we have 2 to the 3 here. There's going to be 3 plus 1. There's nothing else to multiply it by, but 4 factors. And so the answer is going to be 4. So here's a lot of math theory to get the answer. Now, you probably didn't do it this way. What is the answer, by the way? That'll be C. You probably didn't do it that way, but you know, this is how you would do it if you were writing an upper year contest. This has got some math theory. It's got some actual meat in it. It's a very useful method, prime factorization, this sort of stuff. But let's take a look at another easier way to do this specific example. Okay, how about we just list the factors and see which numbers are in both lists? So factors of 40, factors of 72. So what are the factors of 40? Now, you know, you can, the problem with this is what if I miss, what if I don't list an appropriate factor, okay? So you have to use a bit of trial and error. You can also use that, that technique I just showed you. I know 40 is 2 cubed times 5 to the 1, so there should be 3 plus 1 times 1 plus 1. There should be 8 factors of 40. That's a great way to test whether or not we missed one in the list. 1, 2, 4, 5, 8, 10, 20, 40. How about 72? Well, that's 2 cubed, 3 squared, so it's going to be 3 plus 1 times 2 plus 1. That's going to have 12 factors. So that can help us make sure we haven't missed anything. 1, 2, 3, 4, no 5s. 6 certainly is a factor. 6, no 7, 8, 9, 12, 18. We'll write these numbers a little further apart. 12, 18, 24, 36, and 72. So now we just go through with a pen and say, okay, 1's on both lists, 2's on both lists, 3 isn't, 4 is, 8 is, and we check, there's nothing else, so 4 factors. And once again, we could write C as our final answer. Okay, so that's 2 ways to go about doing it: list way, or some really nice, rich, deep math theory about common divisors, counting factors with prime factorization, some really neat stuff that isn't necessarily important to doing this particular question, but is something that you'd like to, you really should start getting exposed to if you want to keep doing math contests. Because on something like a Cayley or a Fermat, they might be dealing with numbers like 40,000 and 72 to the power of 3, those sorts of things. Really big numbers where we couldn't list everything out. Okay? That's why we developed math theory in the first place, because sometimes the numbers just get too big. Or the shapes and the figures get too weird to actually make in reality. That's the whole reason for math theory. Okay? But that was what question? That was 15, wasn't it? Yeah, it was question 15. So in the next video, we're going to take a look at question 16. I hope to see you there.